Good morning, ladies and gentlemen. Today we are going to talk about the second part of our thermodynamics lesson, which is about the ideal gas laws. Now, you've already learned a little bit about the ideal gas laws, but we're going to look at them a little bit more in depth today. So last year, you learned about Boyles Law, Charles Law, and BACS Law. So let's recap those a little bit. Boyles Law states that if temperature is constant, then pressure and volume are inversely related to each other. And let's take a quick look at an example of that in this part right over here. Okay, so over here we have a gas molecules in a container with a movable piston. Now, before we actually talk more about Boyles Law, we should define what does pressure actually mean. When I talk about the word pressure, what is pressure? Well, pressure, ultimately, if you think about from fluids, is a force applied onto a specific area. And every time one of these balls hit the wall, the molecule is applying a force onto the surface, onto the side of the container. It's actually pushing out. That's the pressure that we're talking about. So pressure is when the molecules are striking against the surface of container. Okay, so every time it strikes, a little bit of pressure exerted. Of course, there's a lot of molecules striking a lot of times. But right now, our representation is of just a few molecules. So why would changing the volume change the pressure? Well, let's take a look and see what happens when you decrease the volume of the system. When you decrease the volume of the system, what exactly is happening? And you can see that now these molecules are striking against the walls much more often than before, simply because there's less space. And that exactly is what Boyles Law is about. The pressure will increase as the volume decreases. And we saw that in a graph over here as well. As the volume was decreasing, the pressure was increasing the entire time. Okay? So Boyles Law ultimately is about the inverse relationship between pressure and volume. If we take a quick look over here, right now we have an inflated balloon inside a glass container. And, well, they attach a vacuum pump to it, but let me just preface this by saying a couple of things. Right now, inside the balloon, we have gas molecules that are bouncing around and creating a pressure as they bounce against the sides of the balloon. So there's a pressure inside. And outside, of course, we have gas molecules as well. And they are applying a pressure from the other direction. And those two pressures are going to cancel each other out, which is why the balloon stays exactly the same shape that it does. But now they're going to actually use a vacuum pump to get rid of the air outside of the balloon, and let's see what happens. As you guys can see, as the pressure outside is decreasing, the volume of the balloon is increasing and increasing. And this is just a quick example of Boyles Law. And afterwards, they let the air back into the glass jar, and the balloon shrinks down to its original size. So as the pressure went up, the volume went down. And now we are going to talk about Charles' law. Okay, Charles' law talks about the relationship between temperature and pressure, assuming that volume is held constant. So if volume is constant, then temperature and pressure are directly related. Now, why might that be? Let's go back to our animation and take a look. So right now, before we actually talk about the relationship between temperature and pressure, let's define temperature. Temperature is defined as a measurement of the average kinetic energy of the molecules. In other words, it's how fast they're going. And if you increase the temperature of the system, we're simply going to be increasing their speed. So why exactly would this increase the pressure? Well, as you see, the molecules are now moving faster than before. They're bouncing off the walls more often than before. So as the temperature increased, we can see over here in the graph that the pressure increased as well. The volume was held constant, which is why the line went vertical, but there's clearly a direct relationship between the pressure and temperature. And let's take a quick look at this experiment. Let me just preface this. This is a very common experiment where this is how you can get a hard-boiled egg inside a glass jar. Move this to the side. Let's take a look.
As it cools, it gets smaller, contracts upon itself. What you'll need for this experiment is a glass bottle with an opening slightly smaller than a hard-boiled egg. You'll need a hard-boiled egg with the shell removed, some matches, and a piece of paper. What we're going to do is light the paper, put it down in the bottle. As it's down in the bottle burning, it's going to heat the gas in the bottle, and that will make the gas expand and come out of the bottle. We're going to put the egg then on top of the bottle, and you'll actually see the egg kind of floating or being pushed up a little bit as the flame is still burning and pushing the gas out. After the flame goes out, the gas inside will no longer be expanding.
So you guys saw right here the eggs being sucked in. Why exactly did the egg just go in all of a sudden? Well, when the temperature was high, the pressure inside the bottle was very high. Okay? And the problem is that, well, when you have high pressure here and the gas was escaping out, then you have the two pressures were equal. But as soon as the flame went out, the temperature decreased. And when the temperature decreased, the pressure decreased. So now we have a high pressure on the outside, a low pressure on the inside. So just like with Bernoulli, when we saw how air moves from high pressure, low pressure, the air literally pushed the egg to go in.
Create a negative pressure or pressure smaller than the outside the bottle or a vacuum, and it'll actually pull the egg down into the bottle.
Okay. And our final gas law is BACS Law, which talks about the relationship between temperature and volume. So, assuming, of course, that as pressure is constant, temperature and volume are directly related to each other. And rather than animation, let's take a quick look at this right here. Now, you've actually seen this before with the steel drum, but it's exactly the same idea, where we have a person who takes water, puts it inside a soda can, and then he's going to put the soda can on top of the burner. So the water is getting hotter and hotter and hotter until it's boiling inside. When the temperature cools off, instantly the volume decreases. Okay? And the volume decreased in order to keep the pressure the same inside. Because technically, as temperature goes down, pressure goes down. But the air around doesn't want that to happen, so it will literally crush the can in. So that way now, with the can being crushed, the pressure inside the can is the same as the pressure outside the can. And the air outside just pushed it in. Okay, so that's the ideal gas law. And last year you learned about how they can be related for situations where you set them equal to each other, and we're going to do that in a moment. But the actual ideal gas law looks like this. All three gas laws combined create PV equals to nRT. N is the number of moles of the gas. R is the universal gas constant. And R is always going to be on your reference table as 8.31 joules per mole Kelvin. Okay? So when you're using the ideal gas law, okay, you have to make sure your units are in their proper form. Because we are dealing with joules, we are dealing with kinematics units. So when we're dealing with pressure, of course is going to be measured in newtons per meter squared. Volume is going to be measured in meters cubed. And temperature, because of the Kelvin over here, must be measured in Kelvin when you actually do your problems. And let's try this formula a couple times. If the pressure exerted by a gas at 25 degrees Celsius, so the first given is temperature equals 25 degrees Celsius. But the problem is that we don't use Celsius anymore, we're going to use Kelvin. So 25 degrees Celsius is the same thing as 298 Kelvin because we're adding 273. The volume is 0.044 meters cubed. Excuse me. And the pressure is 3.81 atm. Now we don't use atmospheric pressure, we use newtons per meter squared or pascals. So we multiply that by times 10 to the fifth. So this is the same thing as saying 3.81 times 10 to the fifth pascals, or newtons per meter squared. They're asking us to calculate the number of moles. They're asking us to solve for N. So if we take this and we plug it all in with the formula PV equals to nRT, we can see that N is equal to PV over RT, which is equal to 3.81 times 10 to the fifth newtons per meter squared times 0.044 meters cubed divided by 8.31 joules per mole Kelvin times 298 Kelvin, and the unit you're left with is moles, and you're left with 6.77 moles. We'll do one more practice question. We'll take a look at number 2. With number 2, they ask us to calculate the volume. So in this case over here, they already tell us the number of moles is 0.323 moles. They give us the temperature in its proper form, 265 Kelvin, but they say that the pressure is 0.9 atm. So make sure you convert that into 0.9 times 10 to the 5th newtons per meter squared. And now we can properly solve for the volume. So when you plug this all in, volume is simply equal to nRT divided by P. You plug in your numbers and you get 0.0079 meters cubed. Okay, and now we are going to talk about how we manipulate the ideal gas law like you guys did in chemistry last year. So the main idea here is that if we are dealing with a fixed amount of gas, what exactly happens to the ideal gas law? Well, taking a look at the formula, PV equals to nRT. We already know that R is a constant, it's a universal gas constant, and if N was kept constant as well, I know that NR, if I were to manipulate this, is simply equal to PV over T. And because NR is unchangeable, I can set PV over T equals to a second idea of PV over T, meaning I get that P1V1 over T1 equals to P2V2 over T2. And this is what you guys did in chemistry last year. The most common type of question with P1V1 over T1 equaling to P2V2 over T2 is a multiplier question. Now, if the pressure of an ideal gas held in a vessel is halved while the volume is quadrupled, what happens to its temperature? Now, this is a multiplier question, but it's done a little bit differently, mainly because we don't want to know what the final multiplier is. Rather, we want to cancel out whatever multiplier is happening. Now, what does that mean? Well, keeping in mind that NR is equal to P1V1 over T1, right? That's the original pressure, original volume, and original temperature. That has to be held constant, meaning that if we're going to change up a few variables and have it equal to P2V2 over T2, now if the pressure is halved, that means I have 1/2 the pressure. The volume is quadrupled, I have 4 times the volume. So the key question is what number do I put in front of the temperature to cancel out all of the multipliers so that way this number does not change? So 1/2 times 4 is 2. So if I double the temperature, I will cancel out all of the multipliers, meaning that the temperature must have doubled as well. Okay, so the most common type of question with this is going to be the multiplier question, and keep in mind that you are looking to cancel out all of the all of the multipliers. Remember, however, that if you are going to do this mathematically, you have to use the proper units. Okay, temperature must be in Kelvin, pressure must be in newtons per meter squared or pascals, and volume should be in meters cubed. Now, in reality, if you don't convert pressure or volume, it's not that big of a deal because those units are going to cancel out anyway. But temperature is the most important one. No matter what, temperature must always be in Kelvin. Okay, and make sure you convert before you plug into the equation itself. Now, if we just do a quick practice problem with this. A sample of gas of unknown pressure occupies 0.766 meters cubed. So my first volume is 0.766 meters cubed. I know that it's at a temperature of 298 Kelvin. That same sample of gas, meaning that the number of moles N stays the same, is then tested under known conditions and has a pressure. So this is the second pressure, P2, is equal to 3.26 times 10 to the 4th pascals. The new volume is 0.644 meters cubed, and this is held at a new temperature of 303 Kelvin. So if I'm trying to do this mathematically, I know that P1 V1 over T1 is equal to P2 V2 over T2. Their ask is, what was the original pressure? What was P1? So keep in mind that because of the equal sign, we can simply cross multiply, meaning that we can bring the temperature 1 to the top and the V1 all the way to the bottom. So we end up with a manipulated formula that looks like P1 equals to P2 V2 T1 over T2 V1. And I know it's going to be a little bit messy plugging in all those numbers, but once you plug those numbers in and all the units cancel out, we get P1 is equal to 2.61 times 10 to the 4th pascals. So it's very straightforward. You just have to be careful about your units. In this case, all the units were in their proper form, but if you're doing a question which is not, for example, the following question, you have to be careful. So this temperature would have to be converted into Kelvin. So 273 Kelvin, so 273 plus 36 would equal to 309 Kelvin. Okay, and when you take the 28 degrees Celsius, you want to convert that as well. 273 plus the 28, you get 301 Kelvin. Okay, so make sure that you always convert, especially temperature, when you are doing ideal gas law questions.